Chapter 11. Kinetic molecular theory of solids and liquids and solids. So now we're talking particles are still in motion, right? We talked about kinetic energy and gases moving. They're still moving in liquids and solids, but those intermolecular forces are really strong. So in the solids, they are holding the atoms in place or molecules in place, and they just vibrate in place. For the liquids, they're able to slide past each other. Intramolecular forces. When we're talking intramolecular forces, we're really only talking about covalent bonds. Just as a, because of the definition of intramolecular. What else do we lump in there? We lump in there ionic bonds, electrostatic forces, metallic bonds, anything that kind of holds materials together. Intermolecular forces, our IMFs, are these down here. Our dipole-dipole, dispersion, and H bonding. Who has dispersion forces? All covalent molecules do. Right? They're the only ones that nonpolar molecules have. Right? I'll also write polar there. What's dipole-dipole? Who has that? Polar. Every time I hear dipole, I'm thinking polar. Right? And then H bonding is what? That's a special type of dipole-dipole. For hydrogen bonding, who is hydrogen? How does that work? Just two hydrogens near each other? What is it? What elements do I need? Why is it NO or F? The most electronegative, highest effective nuclear charge, pulling the electrons in. So it makes a really polarized bond. So I could have something like HF, and then I can have O bonded to H, and then the neighboring NO or F to it. Normally we just show water molecules, usually hydrogen bonding to each other, right? Something like this. Something like that. But we could also have HF in there. Those tend to be really strong, attractive forces. Dispersion forces. How do we quantify dispersion forces? Like, how do we know, like, if something's going to have strong dispersion forces or weak dispersion forces? Number of electrons. And the perfect example is the halogens. All of them are nonpolar, right? They're diatomic, nonpolar molecules. So the only thing they have is dispersion forces. I look at the top, fluorine, and then chlorine, gases. Then I go to bromine. I have a lot more electrons there. And now the intermolecular forces really jumped up, and now it went from a gas to a liquid, showing those are stronger intermolecular forces. I go down one more group. Now I have iodine, which is a solid. Really strong intermolecular forces holding those particles as a solid. All right. So in general, dispersion forces are the weakest, but if we have enough electrons there, they can be significant. Then dipole-dipole, then hydrogen bonding. All of these forces lead to the properties of our liquids. High surface tension, right? Surface tension, the attractive forces at the surface and underneath, holding those particles in place at the surface. Capillary action, water molecules trying to climb up the walls of the container, right? If we had a really narrow glass tube, it can climb up there. Due to the cohesive and adhesive forces, the forces of water molecules liking each other. Adhesive forces, the water molecules liking like the glass walls of the container. That's what forms our meniscus. Viscosity, that's a resistance to flow. Stuff that has really high intermolecular forces have high viscosity. Weak intermolecular forces, low viscosity. Types of crystals. Two of these are really easy. Yeah. Those are covalent intermolecular forces, yeah. And just dispersion, we could also put atoms in there. Like if we just had like the noble gases or something like that. Noble gases we can get to turn into a liquid if we put enough pressure on them. And the reason why is because they can have that instantaneous dipole of just the electron shifting. Right? They often use the word polarizability on the AP test. I would say the iodine molecules, those electrons are more polarizable than fluorine's electrons. There's more electrons farther from the nucleus. They're more polarizable. All right. Types of crystals. The easy ones. What is an ionic crystal? What is it held together by? Ionic bonds. We also say electrostatic forces, right? Something easy like that. Yep. Metallic. What holds metallic solids together? Metallic bonds. All right, so those are the easy ones. These ones seem related, covalent and molecular. Right? We're picturing our solid, right? We got a bunch of circles, kind of like this, right? And there's some kind of attractive forces between these, right? There's attractive forces there. And we're saying, what are those attractive forces? In ionic, it's that electrostatic force, right? Positive, negatives attracting each other. In metallic, they're metallic bonds. In molecular, those are our IMFs. IMFs are generally considered weak, so we consider molecular crystals usually aren't very hard. They're usually softer, they usually have low melting points, low boiling points, because there's just weak attraction between those particles. Covalent crystals have covalent bonds between each of these, right? And that's like our diamond or something like that, where there's these strong covalent bonds holding the entire structure together. These generally have high melting points as well. Amorphous solids, these don't arrange themselves like this. They just slow down and stop as they are. All right. Our good example is glass, right? When we break glass, it doesn't break uniformly, it just splinters out for the weakest parts. If we broke like a salt crystal or we break an ionic compound, we usually get some flat surfaces because of just how it breaks in how it's set up. Phase changes, heating, cooling curves. All right. We might have a heating curve that looks like this. Right? This is our heating curve where we have solid, liquid, gas. What process is happening here? Going from solid to liquid. Melting, going from liquid to gas. Boiling or vaporization, something like that. Why is the boil line so much bigger than the melting line? We got to completely overcome the intermolecular forces to go from a liquid to a gas. Solid to liquid, they're still really close together. The intermolecular forces are still really important. They're significant. Here, we're completely overcoming those. If we were to have to calculate this is where we would use a Q equals MC delta T anytime we get a temperature change. So if we're heating the solid, if we're heating the liquid, if we're heating the gas. We can't use that for our phase changes. Why not? Is the temperature changing? No. Instead, here we're going to use the heat of fusion in the heat of vaporization. Right. And those are just like a simple dimensional analysis. These are measured in like kilojoules per mole. So if you have the grams, you convert grams to moles and then just get the kilojoules that way. These ones we would use Q equals MC delta T if we had to do something like that. Phase diagrams. Right. Phase diagrams, we have our solid, our liquid, and our gas. We have temperature and pressure. So it shows the relationship between temperature and pressure. This shows like if we just had a gas at a particular temperature, right? How can I get that to turn into a liquid? I can increase the pressure. and I can get it to condense into a liquid, right? I'm pushing all those gas molecules together into a smaller and smaller volume. Eventually, they condense into a liquid. Obviously, I can also cool it down into a liquid, cool it down into a solid. What's this point here? What's going on there? Triple point. Everything's going on there, right? All phase changes, all states of matter are right there. All right. This also shows how the boiling point is based on the pressure. If we had our regular atmospheric pressure here, right, 1 atmosphere, this right here would be our boiling point. Right? It's that equilibrium between gas and liquid. We go up in a hot air balloon. What happens to the outside pressure? Decreases, right? So now, what's happened to my boiling point? It also decreases, because when a substance boils, that's when its vapor pressure equals the atmospheric pressure. Vapor pressure is the pressure of the material evaporating and creating the pressure there. Once it equals the atmospheric pressure, we can get boiling to occur. This is also how we can also use it in the reverse for pressure cookers, right? We could raise the pressure in there and get it to boil at a higher temperature, so we have to cook it for less time because more energy is getting into the food. All right, anything on chapter 11? Good? All right. Chapter 12. Chapter 12 we went through quickly. There's not a ton there. Solutions, saturated, unsaturated, supersaturated. We had our solubility curves, right? We had like a bunch of different materials on there. Maybe something like that. Right? And these just shows the solubility of different salts at different temperatures. Right? If we were under one of these lines, we are considered unsaturated because we could add more solute and it's still going to dissolve. If we're on one of these lines, we have a saturated solution, right? It can't dissolve anymore. Let's say I'm focused on this line right here, and I add this much of it. What happens? I don't get a supersaturated solution. What do I get? I get a saturated solution with this amount of excess on the bottom. How could I get all that to dissolve? I heat it up, it all dissolves. Now if I cool it back down, now I can have a supersaturated solution. Right? If I put one little seed crystal in there, right, whatever this material is, if I take 1 grain of salt and put it in there, that excess is going to precipitate out on it. That's how we grow crystals. That's how we make rock candy, is that supersaturated solution, and then we put a seed crystal in there to get it all out. Right. Molecular view of the solution process. This takes place in 3 steps. Right. First step, we have solvent attraction that we have to overcome. Anytime we have to overcome attractive forces, that's going to be an endothermic process. That's going to take energy to do. If I have to overcome those solvent, what else do I have to overcome? I have to overcome solute. That's also a positive value. But now I'm getting new attractive forces, new bonds forming. Not really bonding, but we can think of as strong attractive forces. Anytime new ones form, that's a negative value. So my heat of solution is when I add these 3 together. If I get a negative heat of solution, that must mean there's really strong attraction between the solute and solvent, and that's going to release energy. If there's stronger attraction here, weaker attraction there, I'm going to end up with a positive value for my heat of solution. If there's really weak attraction here, what happens? Nothing. The solute just sinks down and doesn't dissolve. Right? We would be insoluble. If there's weak attraction there, maybe some of these are really attractive compared to that. Right? But we got to think of it as 3 steps here: overcoming, those two and forming that one. Miscible just means we can mix two liquids in any concentration and they'll mix together. Solvation, that's that same idea of hydration, where we have solute particles surrounded by solvent particles, keeping them away from each other. Next section was on concentration. All right, percent by mass, part over the total times 100. And since it's by mass, we're talking about grams. Right? Grams of whatever we want over the total times 100. Mole fraction is the same thing, just dealing with moles and not multiplying by 100, not turning it into a percent. So we might leave it as like 0.25 is the mole fraction. Molarity, we're very familiar with, I hope, at this point. Moles per liter, we're not getting confused with moles. And molality, we don't use. Temperature and solubility. From our solubility curve, we see that, in general, as we increase the temperature, our solubility also increases. That is for solids. For solids, as temperature increases, solubility increases. Particles are moving around, they can keep them away from each other more. Fractional crystallization is just that idea that we can separate the mixture based on the solubilities. Right? It's just another way to separate mixtures. Gas solubility. Gas solubility is the opposite of solid solubility. Gas solubility looks like something like this. All right. Here's temperature. Here's solubility. Solubility decreases as you increase in temperature. And the solubility of gases is usually about 1,000 to 10,000 times less than ionic compounds in water. Right? It's just usually they're a gas because they have weak intermolecular forces. Right? So they're not going to have strong dipole or hydrogen bonding, so they're not going to mix with water well. So we're only going to get a little bit in there. And as we increase temperature, the particles move around more, and they're able to get to the surface and have enough energy to vaporize. A good example here is if you open a soda at room temperature versus a cold one. The cold one, there's much less of a chance of overflowing or the soda coming out of the can or the bottle. Henry's law. This has to do with pressure and solubility. All right, and we're talking pressure, so we're only talking gases. The perfect example here is the 2-liter bottle of soda. Right, that's initially under a lot of pressure. Right, you can't squeeze it; there's under a lot of pressure, so there's a lot of carbon dioxide forced into the soda. When I open it, what happens? A lot of those carbon dioxide bubbles come out. Why? Because there's a less pressure pushing down on it. The higher the pressure, the higher the solubility. That's Henry's law. Lower the pressure, lower the solubility. Colligative properties, we don't need to worry about those. Good on chapter 12? Chapter 13, we're already past the midterm. All right. Reaction rates, rate constant, rate laws. So the big part of this chapter was the rate laws. Rate laws look something like rate equals K times A to some power, B to some power, right? And we might have an equation 2A plus 3B yields something. All right. X is not 2 necessarily. Y is not 3. All right. This is the overall equation. How do we get X and Y? We need to look at experimental data. So the way that we saw this was we would have a table that had like concentration of A, concentration of B, and the rate. Right? Trial 1, 0.1, 0.1, and we get a value here, 4. 0.2, 0.1, and we get 8. 0.2, 0.2, we get 8. And from this, we could figure out what the order of each reactant is, right? Looking at these two here, between A and B, right? We could put K remember doing this kind of thing? We usually didn't show it all out. I'm going to do rate 2 over rate 1. So if I had something like this, I could plug numbers in. B stays constant. That drops out. K stays constant. That drops out. But now, my rate, 8 over 4, equals 0.2 over 0.1. To the x, we get 2 equals 2 to the x equals 1. Do we remember that one?
Yeah.
All right. Then we can do the same thing for b, right? If I looked at 2 and 3, I doubled the amount of b. What happened to my rate? So what's the order for b? All right. So we could do what we just did, what we just said for b. As long as you wrote that out, that's fine. That's justification. This is also justification showing it math-wise. Either one is okay. Right. So then our overall would just be rate equals k times a. Right. That's all it would be from that. We would consider this then first order reaction, first order with respect to A. Right. The order of the reactions. If B was also first order, overall order would be second order, because we just add together x plus y. The rate constant, right? We got to figure out the units for that one. That one has units. We just got to make sure the units of the rate on one side equals the units for the rate law on the other side. On the AP test, this is what we get, right? So we don't see the rate law itself, but the rate law I think we got. Here, this is for 0 order, right? This is for first order, second order, right? And this is the half-life for first order. Right. This is the ones that we get. This data is concentration and time data. Concentration and time. The data that we just looked at was concentration and rate data. Yes? So it's kind of like two ways to look at, right? They're related, the integrated form of it, fine. What we got here? So first order, second order, half-life, the time it takes for half to decompose. Activation energy. How does activation energy play a role in these reactions? Right, the higher this is, the slower the reaction is going to be. The lower the K value, the rate constant is going to be. So activation energy, it can be a higher value. As temperature increases, what happens to activation energy? Stays the same. Nothing happens to activation energy. But my collisions now, they're colliding with more effort or with more force, and it's more likely to get that reaction to occur. All right, at the higher temperatures. All right, reaction mechanism and elementary steps. This is where we get into our rate law being consistent with the slow step. Do we remember that? Right, we might have like A goes to C. A plus C plus B yields D. Right? 2B plus D yields E, something like that. And we can add all those up, we'll get the overall equation. Whatever the slow step is consistent with the rate law. What did our rate law say? The one that we just made up there? That it's first order with respect to A, right? That must mean this right here is the slow step. Whatever the reactants are of the slow step, that is consistent with the rate law. If there was a B in that one, it would be first order with A, first order with B. If it was 2A, it would be second order for A. But that's always the slow step. So they would tell you that slow step. What's an intermediate here? C and D, because those were both produced and consumed within the reaction mechanism. The rate determining step, that's the slow step. If I have data for concentration and time data, right, I'm going to graph that data, the concentration versus time. That's how I get whether it's zero, first, or second order. If I graph this data and it's linear, that's zero order. If I graph that data for first or second order, it looks something like that. All right. First and second look about the same. No, it happened in the overall equation, so it's still going to get used up. It just won't get used up as fast as A will.
So the catalyst is on both sides of the equation.
Right, like if we had a catalyst, we could put it like G up on top or something like that.
Oh, yeah.
So what I would take then is, if I wanted to see if it was first order, I would graph what? Natural log of concentration versus time. Do we remember this? And for second order, what is it? So that's here. That's in these equations right here, right? Just concentration versus time is linear. Natural log of concentration versus time is linear for first order. 1 over concentration versus time is linear for second order. Last up, catalysts, enzymes. Catalysts do what? They speed up the reaction by lowering the activation energy. They change this pathway. Whatever that slow step is, they make it a little bit faster. So if I were to show what the catalyst looked like, I would start in the same spot, and I would finish in the same spot. But I would have lower activation energy, and I would get there faster. Right? Still starting and finishing in the same spot. What are enzymes then? Yeah, like usually big proteins in our bodies. Those are our enzymes. Where catalysts, when we're talking chemistry, are usually simple, ionic compounds or something like that. Is it a good stopping point?
Yeah.
Yes.
For the half-life equations, do you need to know the zero and second order?
Nope.
The only difference.
Wait, what's the difference between intro and intermolecular?